Today, we cover section 7.8, improper integrals. So to motivate, I pose the following problem. Let's consider a curve y equals 1 over x squared. Okay. Obviously, it blows up at 0, but let's start at 1. Okay. And let's try to calculate the integral, or the area rather, under this curve from 1 all the way to infinity. It may seem like a silly question, because if you have an infinitely long shape, how can it have a finite area, right? So amazingly, it's sometimes possible to calculate a finite area for an infinite shape. And so let's think about this. So let's set the right limit of integration to be a variable t, okay? And we can calculate the area between 1 and this moving, shifting right boundary t. So for instance, when t is situated here, this is the area between this vertical line and this vertical line. Okay. So the area under the curve x squared. So this is a definite integral. We can evaluate the antiderivative from 1 to t. So that's it's minus 1 over t plus 1. Okay. So for each position of the right boundary of my shape, I know the answer. I know the area. For example, if t equals 2, a of 2 is 1. So I can say 1 minus 1 over t. 1 over 1 half is 1 half. T equals 3. The area is 1 minus 1/3. So it's 2/3. T equals 4. A of 4 is 3/4. Okay, 5. A of 5 is 1 minus 1/5 is 4/5. So we have 1 half, 2/3, 3/4, 4/5. You can see that it gets bigger and bigger, but it has a finite limit, right? As I shift this boundary to go from 2 to 3 to 4 to 5, the total area increases, but you can see that it doesn't increase without bound. Where is the limit? 1, right? So we can say that the limit as t goes to infinity of a of t is the same as the limit of 1 minus 1 over t is 1. So we define the area under the curve, and we denote it as an integral between 1 and infinity dx x squared to be equal to 1. Right? So this introduces two things. The process, so I take a variable upper limit and I take the limit, and it introduces the notation, an integral whose upper limit is not a number, it's an infinity. And this is what it's an example of an improper integral. So in general, there are several types of improper integrals. So improper say of type 1. Type 1 is when we have the area of the range of integration that is infinite. Okay, there are 3 kinds of infinity that we're going to consider. An integral from a number to infinity. So we go infinitely far to the right, or we can go from minus infinity to a number. So we go left infinitely far. or we can go from minus infinity to infinity. These are three basic types of this type of improper integrals. Okay, f of x dx. And they are defined in the following way. So this one, the lower limit is a constant. That's fine. Sorry. The lower limit is a constant. The upper limit we call t. Okay. And we calculate this as a regular, proper, definite integral. And then we take the limit of t going to infinity. So this is a definition of the symbol in the procedure I already described to you. Here we replace the lower limit with a constant. So it's the limit from t, so the integral goes from t to b. And the limit is from as t goes to minus infinity. Okay. And this one is a combination of the previous two types because it has two infinite limits. So what we're going to take, what we're going to do here, we're going to break this integral into two. We're going to integrate first from minus infinity to a, where a is any number. Okay. And then we'll continue from a all the way up to infinity. And I already defined these two for you. So a very important thing to say is that this improper integral is only defined if the limit exists and is a finite number. So here I say if the limit exists and is a finite number. In this case, the integral converges. Otherwise, the integral diverges. So if we see that the appropriate limit doesn't exist as a finite number, either it doesn't exist at all or if it's equal to infinity, then we simply say that the improper integral diverges. There is no answer. Question?
For b, why is it the negative limit as t approaches negative?
Oh, it's not. Thank you so much. Yeah, the negative sign is here. More questions? Oh, yeah?
For c, why isn't it the limit of the integral?
So here, it's a slightly different procedure. So first I look at this, and I break it into two improper integrals. So I go from minus infinity to a constant, plus from the same constant to infinity. So I cut this in two. And then these two are defined as limits. Okay? More questions? So let's look at an example. We already had one example here. I want to show you a different example, which looks very similar. So calculate an integral from 1 to infinity of 1 over x dx. What's the difference? Here we had 1 over x squared. Okay? In the new example, I have 1 over x. So you can see that this is an improper integral of type 1a, where I go to the right. The upper limit is infinite. So I can say that this is a limit as t goes to infinity, an integral from 1 to t dx over x, right? Now, what's the antiderivative here? It's the log. So limit as t goes to infinity of the log of x substituted at 1 and t. I continue to write. So I have log t minus log 1. Okay. So log 1 is simply 0. I don't have to worry about it. How about log t? What's the limit? it's infinity, right? Remember the log blows up. It goes to infinity as the argument goes to infinity. So what can we say about this improper integral? It diverges. The integral diverges. Okay. Now we see something very strange. This guy converges, and the area is 1. I change it a little bit. Instead of 1 over x squared, I take 1 over x. And this, if I drew a graph, it would look the same, right? Because I don't have a scale. What's the graph of 1 over x? It's like this, right? So this area apparently is infinite. Okay? How can this be? And it's not a simple thing to explain. Somehow, you can see that this falls off and becomes thinner and thinner and thinner. And when x is very large, the function becomes very small. And somehow, the area sums up to a finite number. This one also becomes thinner and thinner and thinner, but not fast enough. So let's compare the two lines, actually, instead of plotting them separately. What's the difference? So at point 1, let's suppose that this is 1, and this is 1. So at x equals 1, both lines, 1 over x squared and 1 over x, pass through the same point. Now, when the argument is 10, 1 over x squared is going to be equal to 1 over 10. 1 over x squared is going to be 1 over 100. This is completely not to scale, right? I cannot draw it to scale, but something like this. When this is 100, this guy is 1 over 100. This guy is 1 over what? 10,000. So in fact, this is 1 over x squared, and this is 1 over x. This is a lot thinner, right? So somehow it works out that this sums up to a finite number equals 1, and this one diverges. Okay? So an interesting question is, when we look at all such curves, when do they converge and when do they diverge? So this is the question that we pose next. Consider an integral from 1 to infinity. Let's see, of 1 over x to p dx. And we assume that p is not equal to 1. We already know what happens when p is equal to 1. For what values of p does the integral converge? That's the question. Okay, I'm not going to handle the case when p equals 1. That's a special case when we have a log. So we know that for p equals 1, for p equals 1, it diverges. For p not equal to 1, what do we have? We have the limit. So 1 over x to the p dx is equal to the limit as t goes to infinity from 1 to t. And here we can say x to the minus p dx. So we can take the antiderivative, t to infinity, x to the minus p plus 1 minus p plus 1, evaluated at 1 and t. Fine. So I continue to write 1 minus p. This is just the number. The limit as t goes to infinity of t 1 minus p minus 1. So when is this finite? what can we say about the value of p that makes this finite? So t goes to infinity. I want this guy to stay finite. If I have a number, okay, let's think of it as 1, 10, 100, 1,000, and so on, raised to a power. If this power is greater than 1, what happens? It grows, right? But if this power is less, did I say 1? If this power is greater than 0, it grows. If this power is negative, though, I have a decaying function, right? So this quantity has a limit plus infinity if the power is greater than 0. And it has a limit of 0 if this power is negative. Correct? So this I can invert and say that this is the same as p less than 1, and here p is greater than 1. So to conclude, the integral converges if p is greater than 1, and it diverges if p is less than 1 or equal. We know from before the equality. So if we look at this original expression, a large value of p means that it decays very fast, and then it converges. A small value of p means that it doesn't decay fast enough, and the area becomes infinite. Questions? OK. Very good. So another example I will give is type C integral, where we have two infinite limits. And it also involves a trigonometric function. So let's do this. From minus infinity to infinity, 1 plus x squared dx. Okay, so what do we have to do in this case? We have to split it into two integrals, for each of which one limit is finite. You can see that this guy is symmetric, actually. I'm going to split it at 0. But so we can write it as an integral from minus infinity to minus 27, right? Plus an integral from minus 27 to infinity. You would still get the same answer, right? It doesn't matter. So to make my calculations easy, I'm not going to use 27. I'm going to say that this is an integral from minus infinity to 0, and from 0 to infinity. Okay, so let's do this one. This is from minus infinity to 0 is the limit as t goes to minus infinity of an integral from t to 0 dx 1 plus x squared. And of course, this is a standard question?
Quick one. Now, I know the rules with infinity are slightly different, but could you, since this is an even function, just say 2 times 0 to infinity?
In principle, I could, with a little bit more work. So if the theorem that we proved last time was, of course, only for finite integrals. And it takes like 2 lines to prove it for an infinite integral. Instead of doing that, I demonstrate the straight calculation. Okay, so but in principle, you're absolutely right. It's a symmetric function.
Okay.
So let's take the antiderivative. T goes to minus infinity. So this is arctangent x from 0 to t. Okay. So the limit is t to minus infinity. So tangent minus 1 of t minus what's arctangent of 0? 0. So I'm going to just say 0 here, right? So what's the limit? you have to recall the shape of tangent and then arctangent. So in this case, when t goes to minus infinity, we have minus pi over 2. Except I exchanged the limits of integration. So it's 0 minus tangent minus 1 of t, like this, sorry. Okay. So it's minus negative pi over 2. It's pi over 2. The second integral goes from 0 to infinity. Now I replace the top limit of integration with a variable. Okay, so I have an arctangent of plus infinity, which is pi over 2. So what's the answer? The answer is the sum of the two. You can see that both parts converge, and the answer is the sum of the two. Not surprising that they are the same, and the answer is pi. So if I were to discover that the first integral diverges, then I wouldn't even have to evaluate the second one, because the answer would be the whole thing diverges, right? Or if I discover that the second one diverges, I would have to conclude that the whole thing diverges. So for convergence of this kind of an integral, I have to require the convergence of both parts. Questions? Okay. So this is not the only type of integrals. The second type goes here. So far we're dealing with infinite ranges of integration. So geometrically speaking, our shapes were extended infinitely in the horizontal direction. Now what if it's extended infinitely in the vertical direction? That gives rise to the second type of improper integrals. Of type 2. To illustrate it with a picture. If I were to integrate the same function, 1 over x squared, but not from 1 to infinity, but between 0 and 1, okay, that's this area. You can see that the function diverges at the left limit of my integration. But if you look at it from a side, it looks very similar to our previous example, right? Except it's in a vertical direction. So this gives rise to the second type of improper integrals. And let's say that, so here we again have A, B, and C. So if f is discontinuous at B, then the integral from A to B becomes improper, okay? And what I need to do is the following. I'm going to replace the upper limit of integration with a symbol t and set up a limiting process, where t approaches b on the left. So here's a picture. The function has a vertical asymptote at b. Okay, so I take t here, and I take a limiting process whereby t increases and approaches b on the left. For each value of t, when it's not equal to b, we have a normal continuous integrand, and we can use a proper integral to evaluate this expression. Then we take the limit. I'll give you examples in just a few seconds. So here, and I imply that everywhere else, obviously, the function is continuous. Okay, I didn't write it down. So if f is discontinuous at a, then an integral from a to b f of x dx is replaced by a limit of an integral from t to b, where t goes to a on the right. So at a, we have a discontinuity, and I set up the variable t that tends to the left. Okay. So each time I have a t that is not equal to a, I have a finite integral, and everything's great. And then I take the limit. Finally, type C happens when the discontinuity is somewhere between a and b. Okay, if f has a discontinuity at c, which belongs to an open interval between a and b. So the function experiences a discontinuity somewhere between its limits of integration. For example, from a to b at point c, we have a discontinuity like this. Okay, what happens? We cannot just ignore it. We have to split this integral into an integral from a to c plus an integral from c to b. And these two types are type A and B, because each of them has a discontinuity at either left or right border of integration. Again, the integral is only defined if the limit exists as a finite number. Exists as a finite number. Otherwise, the integral diverges. Okay. So let's look at some examples. So the first one is the following. So let's integrate from 3 to 6, 1 over square root of x minus 3 dx. Okay. So this innocent-looking integral, of course, has a discontinuity when x equals 3. So whenever you have a difference in the denominator, you have to check if the thing blows up anywhere inside the limit of integration or at one of the ends. Okay. Here, the discontinuity happens at the lower limit of integration, so it is the second type, type B. Okay. We have to worry about the number 3. So we say the limit. So we replace 3 with t. This is 6. And t tends to 3 on the right. Okay. So now, when we ignore the limiting process, this is just a definite integral which is continuous. The integrand is continuous everywhere for any t that is to the right of the number 3, right? So for any value of t, this is a nice, well-behaved function. So we have to take the antiderivative. From t to 6, okay, to limit okay. So what's the limit? T goes to 3, okay? So this is a constant. What is this? What's the limit of this expression? 0. So the answer is 2 square root of 3. Okay, so let's draw a picture here, actually. This is 3, this is 6, and we have 1 over square root. So in principle, we do have one of these shapes, right? It does have a vertical asymptote. But it happens to be a convergent integral. And it's difficult to say in advance, right? And we don't know until we take the limit whether it's going to sum up or not. Okay. Now, the next example is this. This is harder to catch. Let's consider the integral from -2 to 2, 1 over x plus 1 dx. Right? So what's wrong with this one? It has a denominator that turns into 0. Denominator equals 0 at x equal -1. So inside the range of integration, we have a discontinuity. So let me first do this in the wrong way. Okay, this is wrong. If I don't notice this fact, I would go through the motions and just pretend that it's a proper integral. What would I get? This would be a log, okay, of x plus 1 evaluated between -2 and 2. So it's log of 3 minus log of -1 absolute value. So log 3. But so I got a final answer, but this is a meaningless, completely meaningless answer because it's wrong, right? This disregards the fact that the function experiences a discontinuity at -1. So if this is -1 and this is 2, so here we have a vertical asymptote, and the integrand actually looks like this. Okay, so this is the area we are supposed to calculate, and let's see what we get when we approach this problem properly. So, so the correct way requires to split this into two integrals such that we handle the discontinuity explicitly. So first we go from -2 to -1, so that's this branch. And then we go from -1 to 2. And we have to evaluate them separately as improper integrals of types A and type 2A and 2B. So let's do that. So let's do the first one. This is the limit. The problem happens at the upper limit. So t goes to -2 on the left. Okay. I'm sorry, -1. So this is the limit as t goes to -1 of log x plus 1 log of t plus 1 minus log of 1. So this is the expression whose limit we have to handle. What happens to this log when t goes to -1? T goes to -1, the argument of the log goes to 0, and you see immediately that the limit does not exist as a finite number. Diverges. And I don't have to worry about the second part of this integral, because I already know that the original integral diverges. There's nothing we can do. So the original, so we can say that the integral from -2 to 2 of dx x plus 1 diverges. Questions? Okay. Next example. Let's do the following. From 0 to 1, log x dx. Okay? We integrate the log. And if you remember the graph of a log at 1 at 0, and it has a vertical asymptote, it goes to -infinity at 0. So who knows how it will behave in terms of integration, right? Does it diverge or converge? We have to go through the motions. So we replace this with a limit at t approaches to 0 on the right of the integral from t to 1 log x dx. And now we have to remember how to integrate a log. What's the method for integrating the log? By parts. This is by parts. This is a tricky one. You have to say that u is log x and v prime is 1. Remember? And u prime is 1 over x and v is x. It's a hidden integration by parts where you view this as log x times 1, right? So v prime is 1. Okay, you should know this. Now let's do the integration. Log x times x. I'm just doing the antiderivative, right? Minus an integral of 1 over x dx. So the answer is log x times x minus x. So this was what happens when you integrate a log. We're going to use this. Questions? We're going to use this result to evaluate the improper integral. So t goes to 0 plus. I'm going to write down the antiderivative and evaluate it at t and 1. So limit as t goes to 0 plus. So this first part gives me a log of 1 times 1. What's that equal to? 0. Minus 1. Now I have minus log t times t plus t. Fine. So that's correct. Limit t goes 0 plus of t minus 1 minus log t times t. So I know that when t goes to 0, this is 0. So actually, I don't even have to worry about it. I have minus 1. And I have log t times t. So my Friday's lecture comes useful here. Because what happens? When t goes to 0, log goes to minus infinity, and t goes to 0. We have a certain tension here. Who wins? This is your undetermined product. So what is the limit? Is t going to 0 of log t times t? We have to turn this into an indeterminate fraction. Limit of log t divided by 1 over t. And then we take the derivative by using the L'Hopital's rule. So the log, when I differentiate, is 1 over t, and this is minus 1 over t squared. Finally, I simplify. I have minus t, so that's 0. Okay. So when I evaluate the limit, my answer is minus 1, because this guy goes to 0 by using L'Hopital's rule. So this graph, although it has a discontinuity at 0, like this, happens to sum up to a finite number, right? It converges. And of course, the answer is negative. Better be, right? Because the log between 0 and 1 is a negative function. So we can always check the correctness. Questions? Question?
I'm kind of confused. Where did the plus t go? Just go away somehow.
Plus t?
Yeah.
Oh, it's a limit when t goes to 0. So the limit of that guy is 0. More-
But can we just plug in with the
Here?
integral of t times t equals 0? Can you just
Here?
figure that out? Yeah.
So we have a limit of a sum of several things. So a limit of a sum of different functions, you can evaluate each limit separately and then add them up. So this is a 0, this is a constant, this is the difficult one, and this is.
But when you plug in 0, it's still 0. And if you, it's like ln of t multiplied by t.
So when I cannot plug 0 here, because log of 0 is minus infinity. So this is my indeterminate form of the type infinity times 0. And that's why I did it separately by using L'Hopital's rule. Okay. Question?
Yeah, is there absolutely any way to kind of look at it and see whether or not it's going to converge or diverge, except for the power rule?
Experience. You kind of know that logs integrate, and I don't know any other way. But it all goes down to calculating the limits. Okay, so the last thing that I want to mention is a comparison test for improper integrals. So sometimes we cannot evaluate the integral, but we can tell whether it converges or diverges by comparing it with other functions whose properties are easier to study. So comparison implies that we have two objects that we know a relationship between. So comparison. So let's suppose that we have two functions, f and g. And let's suppose that they're both positive and f is bigger. Okay? For x starting at a. So the picture is like this. We have, I don't know, this is a, f, and g is smaller. Sometimes they can be the same, but so this is g. Okay. Now there are two parts of this theorem. If the improper integral of f converges, so if the bigger area exists then for sure the smaller one bounded by the function g will exist too. Then the area under g also converges. Okay. On the other hand, if the integral of g diverges, so we take the smaller area, and we know that it's infinite, the one that is bounded by a larger function, of course, is also going to be infinite. We can say that f dx also diverges. Okay. And I want to do two very quick examples. So the first one, let's consider minus log x 1 plus x squared from 0 to 1. Okay. I have no idea how to take this integral. At least it's not easy. Okay. But we can use a comparison test for this thing. So minus log x, this is a positive function, right? Between 0 and 1, this is going to be smaller or equal to minus log x. Because we divide by something that's bigger than 1, right? This one we don't divide, this we divide, so this is smaller. So this is our function g, the smaller one, this is our function f. And we know something about this function, because we just calculated. We know that an integral of log x dx converges. That was our last example. Just calculated. This is equal to minus 1. This function is minus that. And of course, it also converges. It's equal to plus 1. Okay. So if this converges, then this will also converge. So we can say that this is less or equal to 0 plus 1 minus log x dx. This is equal to 1. Okay. So we conclude that the original integral also converges. With almost no extra work, we're able to show that this complicated integral can be evaluated. And this integral, just like this one, has a discontinuity at 0 because of the log, right? Okay, that's one example. And the second example is very short. Let's look at the integral between 1 and infinity. 5 plus e to the minus x over x dx. Okay. So let's look at the expression. This is not an easy one to calculate. But so we know that we can take 5 over x and add something to it that is positive. So this is definitely bigger than 5 over x, right? For this function, we add stuff in the numerator. Here we don't. Okay? So, and this function is very easy. We know that this integral, 1 over x dx, diverges, right? This corresponds to the power of p equals 1. We proved that this is a divergent integral. Therefore, the integral 5 over x dx also diverges. And this one is even bigger, right? So we can say that this is bigger than 5 over x dx. So this guy diverges. So we can conclude that the original integral also diverges. Thank you. And I'll have a lecture tomorrow during your discussion time. Thank you.